So today we're doing electric field, right? So let me open the slide. So this theory here on electric field, they usually bring it on multiple choice. So you must ensure that you actually know it. So it's that here. So the definition of an electric field is this one. They ask you what's an electric field. You say an electric field is a what physical field that surrounds electrically charged particles. So I'll also try to go to the question paper. Let me see if that paper is there. Okay, let me share question paper here. This one. So here on electric field, you'll have to know what's electrostatics and also know what's an electric field. So let's see this definition. It's a physical field that surrounds it. Yeah, so this one is the definition for electrical field. In case they ask you, we'll say an electric field is a physical field that surrounds electrically charged particles. And then for electrostatics, I'll write the definition here because electrostatics. With this one, you'll see it's a branch in physics that this deals with what? With slowly moving electric charges. Okay. Okay, that deals with. So I'm not gonna stick much on this theory, right? I'm just heading on whatever it's on the slide. Branch in physics that deals with properties of stationary and slowly moving what? Electric charges. Open this. And slowly moving charges. Charges. So this one is the definition for electrostatics, and then this one is the one for electric field. So you'll check those definitions later on. So we've got what to call properties of electric charges. Okay, this one you'll check. It's not much important. Properties of an electric. Okay, this one's they're important. You must know what are the properties of an electric charge. Ne? The first, so there are. Let me see. 1, 2, 3, 4. So the first one they're saying is a charge transfer from one type of material to another. I think this you already know. An important character so that. Okay, another property that is important here is this one. You have to understand that a charge is not created when two neutral objects are rubbed together. Ne? 5, 6. Okay, and then this one, yeah, it's also one of the important properties that a negative charge will be transferred from one object to another when you charge two objects. Then let me see. Then we've got types of those. Yeah, so during charging of electric charges, we've got types of charging. So there are 3. So you must know all of them. So the first one is charging by friction, charging. The second one is charging by conduction, and charging by induction. So with this one, it's whereby you are applying friction between two materials. And then with conduction, this one has to do with, I think it has to do with heat. Let me see the, okay, so this one is an example, it's a diagram, right? So this is silk, and then I don't know what's that, it's a rod, yeah. So this one is an example of charging by friction. Let me see if there is a diagram for conduction. But for conduction, they didn't write. Okay, but you'll have, here you just have to understand the difference between charging by conduction and also charging by induction. So on charging by induction, I think the difference lies between whether the two materials are going to touch each other or not. So on induction, there is no contact with the object. Charging by induction requires no contact. And then with this one, for charging by charging by conduction, there will be a contact. That means a negatively charged metal touches to the neutral sphere, and some of the electrons pass to the sphere. As a result, neutral sphere is negatively charged. So I think here it's a matter of what? Here there is contact, and then here there is no contact. So you must just know that you're there. It's important. And both of them, they are talking about a sphere, for both of them. Even here, we're talking about a charged sphere. So here there is no contact. Electrons are just transferred between two objects without contact. On induction. So there's an example, right? It's a rod, you have a sphere. So some of the electrons here will go to the sphere. Here you have a sphere. And you have got your rod. So the electrons will be redistributed to the sphere on charging by induction. So you must just note them. Okay, let me try to open another this one, because the one I'm using, it was something went wrong. Yeah, now everything is fine. I was struggling to open this thing. Out of storage. Ganja. Okay. Just do this. I wanna use this one because that one is slow, because I cannot scroll downward there. So I wanna try using this one. Still I have a lot of documents. No? Don't think it will open now. Okay. Barata wa dama. Bar disturb. Yo. Guys, just be a little bit patient, ne? I wanna make sure I use this one because the reason I'm very slow is because of that app. So let me try deleting these things. Thought there was still space here. Let's see. Yeah, now it is fine. Yo, what's this? Okay, so what I was saying is that you must know the definition of what electrostatics and the definition of what's that one of electric field. And then this one is the definition for electrostatics. And then I said the most important part on this slide is for you to also know these properties of an electric charge. All of them. Understand how charges are how charges act. And then when a charge is conserved, they can ask you what does it mean, and when a charge is quantized. So when a charge is conserved, what will happen? This implies that a charge cannot be created or destroyed. This one is a law. I think you guys should know that. Is this? This one is a law that if a charge cannot be created or destroyed, then we have a conservation of charge. And then charge is quantized. It means that what will happen, meaning it comes in a distinct amount. All protons carry the same amount as electrons. Here, the electrons will be equal to, they will be equal to electrons. This, the electrons will have the same number of what? Of protons. That's what they mean when they say a charge is quantized. So let me move. Now this thing is working. And then an electric field, you'll just say it's a physical field that surrounds what? Electrical charged particles. Then we'll move. And then we have discussed the types of charges. Nah? This one's charging by friction, charging by conduction, and charging by induction. So you must also know how to mention them. And let me scroll. Then I've explained the differences. Nah? I hope you guys you understood. But let me just repeat because I'm gonna limit this video to certain parts. So with charging by induction, we said the materials they will touch each other. Né? Then by induction, the materials there won't be contact between the rod and the sphere, because this is a scenario of having a rod and a charged rod and a charged sphere. So here there is no contact on induction. Okay, and then with conduction there will be contact. I hope you already understand that. By induction. So I've got different types of materials. So even these ones you must know them. There are three as well. You have got insulators, conductors, and semiconductors. So you'll check the differences, right? I think all of you know what's an insulator, conductor, and semiconductors. Let me see if they give examples. Yeah, they even give examples. With semiconductors, we're talking about silicon. Then with conductors, copper, aluminum, and silver, right? What else? Insulators. We've got glasses, rubber, Insulators are those materials which by you cannot working insurance are materials in which all of the compounds on this have become charged. Guys, I think can you guys give me an example of insulators? But I think you know them, right? They are non-metal. I can say they are non-metal. So you must just know these types of materials, because now we're talking about charges. Then we'll move. We come to Charles column. So the formula is like this. When they ask you to calculate the charge, I think you already know this. Should I add the page? Let me add it here. A Q1 Q2 over R squared 1 2. So this formula, I think you all know it. It's for calculating the force between two charges, right? So another important thing is for you guys to know what is Coulomb's law, knowing how to state it. So let me just write it here. So this is important. They can ask you in the exam this one. State Coulomb's law. So you'll say it's the magnitude of the electrostatic force between 2-point charges. So the magnitude of the electrostatic force between two charges is directly proportional to their product. To their direct proportional to the product of the what of their magnitudes. Of their magnitudes of the charges between of the charges, and then it is inversely proportional to the square of the distance between them. Of the distance between them. So an example, you will be required to calculate the, let's say you have two positive charges, and then you have the distance r, and then what? So obviously they're going to repel each other, right? These ones, they will repel each other. So they're gonna give you the value of Q1, maybe it's 5 nanocoulomb, then this one Q2 being 6 nanocoulomb, then the distance they say 5. So this one is the easiest, né? So everyone should know. Then you write your Coulomb constant, which is this one. Then Q1, the charge is 6 times 10. Okay, there are two. Yeah, it will just be like this. And then all over 5 squared. So this is how you calculate the force between 1 and 2. So your answer, I don't know what answer you'll get, né? But most importantly is to know the direction as well. So let me do this. Let me see on your test one what they were asking, né? I'll have to share this again. Let's check what was there on test one. This app. The first question they were asking about what? So this is the theory that I was talking about. From 1 up to number 4 is the theory that I was talking about. So can you guys try us answering this? Name a charging process where charged rubber is placed near a sphere and it does not touch the sphere. So the answer here was letter C, because what they are saying not touch. You see that theory is very important. And they were saying name a material when a charged particle in a small region, the charge easily distributes itself over the what? So here you are supposed to choose the material. So which material will it be here between these three? And conservative force. You must also know what's conservative force. Hello guys, let's answer these questions, guys, quickly. I want us to also do these examples down here. Let me see. Let me see this part. Electric field, the definition we just wrote it. No? Actually, we can just do the whole correction of this. Just that I don't know if you guys here are busy or what. Number 1, it's C. Guys, let's answer this. Number 2, let's answer this quick. Let me check the chat box and try answering that one, guys. Let me go back. Guys, you guys are not even attempting. Attempt the second one. What's the answer on the second one? It was not supposed to be here. Or at least, if not the second one, the third one. What's a conservative force? Which option are you guys going to choose here? Guys, I need you to participate. Remember this exam preparation. So we're going to be doing a lot of things. So if you're not communicating, even myself, I'll get bored. Or I should just write the answers for you and then you will understand. Remember that we said for a conductor, the materials, they touch each other. Ne? So the answer here is a conductor. It's letter B. A material when, yeah, that one is for a conductor. And number 3, a conservative force. You will choose letter what?
Number 3 is A.
Number 3 is A. The force with the property that work down in moving a particle between 2 points. So this term here is the important term, independent of the path taken. So once you see that, you should know it's that talking about conservative force. So with that one let me go back to that slide so that I didn't download. The thing is loading a lot of times. It's loading this much. My documents are not opening due to the network. not opening. Okay, let me do this. I'll just say it again. Okay, so we say this one, the answer was induction. They do not touch each other. So it's A. Then this one, the answer was conductor. This one we're choosing A because of the term independent. Okay. Yeah, this one it opened. And let me take that. Let me open this slide again. I didn't send. I want us to discuss the differences between those, the conductor, the what, insulator, these ones. Those materials, where are they? Different types of materials. So you must know the difference between an insulator, conductor, and a semiconductor. Because in the multiple choice, you don't know which one to choose, right? Let me see there. That statement on test one, when a good conductor is charged, yeah, it's this one. It says when, for a conductor, they are saying when a good conductor is charged in a small region, the charge readily distributes itself over the entire surface. But with insulators, when a good insulator is charged in a small region, only the area becomes charged and the charge is unable to move to other regions. So this statement here is important. Then with this one, for semiconductors, they are saying the what? For semiconductors, they will be changed over many order of magnitude by adding controlled amount of foreign atoms. Mhm. Okay, so you just had to understand that for a conductor, it will be charged in a small region, né? But this one that becomes charged. And also that the charges will redistribute themselves. But here, the charges won't be able to move on what? On insulator. So that's why that option is a conductor. That's what I'm saying, guys. Make sure you read the theory. Ne? Hey, this thing closed. Hey, let me do this. Yeah, now it's fine. Ish. Yeah, guys, this app is misbehaving today. Yeah, it opened. I think it's because of the network. Okay, so I've answered one and up to three. Let's move. Number four, which of the following is a good is a good example of an insulator? So which one are you guys going to choose there? We've talked about the examples of an insulator. It's aluminum, isn't it? I don't know. Is it aluminum or glass? Between the two. I think which one is a good example? Good example. Uh,
I think it's glass.
It's going to be glass because an insulator is a material which does not allow electric current to flow easily. So the one that will not allow electric current to flow easily will be glass. So here it will be glass. Then let's move to the next one. Oh, today guys, it's been a long day. Then number 5, they were saying consider the two charges Q1 and Q2. The distance between the charges is R, and the force of attraction between them is F. Which of the following proportionality is not correct? The one that is incorrect there. Which one is it? Remember we said Coulomb's law is like this, no? Then squared. So force is directly proportional to Q1. So this one is correct. Inversely proportional to. Then this one is also correct. I'm not sure. I think it's letter C. Do you guys agree that we're gonna choose C?
Yeah, it's C.
Because it's inversely, it will never happen that force is inversely proportional to the product of the two. So this one is incorrect. It's the only one that is incorrect. This one is correct, and also this one is correct. Since these ones, they are on what? Q1 and Q2, they are on the numeric. So the answer is C. Okay, you guys were coming up fine. Then object A has a charge of 2C and object B has a charge of 6C. So both of them, they're positive, and they're saying which statement is true about the electric forces on the object. So here's just a comparison. F1 is 2 coulomb, F2 is 6 coulomb. Fine. Which one is true about the electric forces? The electrical forces. So they just gave us the charges. So they gave us Q1 and Q2. So now they're asking about the force between them. You know, force is given as K Q1 Q2 over R1 squared. So will the force be the same or it will differ? It is going to differ, right? With the sign, I think. Yeah, the charge of 2C. So this I think is based on Newton's law, Newton's third law of motion. You have to know which force between those two charges will be greater. Will they be equal or not? I think that's the first question. Because as you see, this one is 3 times, 3 times, 3 times. So we know that these objects, they are both positive, and you've got another one which is positive, right? And then they will repel each other. That's the first thing you know. So regardless of the magnitude, guys, of the charges, the force will still be the what? It will still be the same. So this is a matter of understanding Newton's third law of motion on this one. So the answer, because you'll be surprised where they're getting this 3, right? So the answer is just letter D on this one. Newton, we're applying Newton's third law of motion. Third law. Remember that they're going to repel each other. That's why this one is negative. Then letter number 7. You have got two charges, a charge for millicoulombs at a distance of 2.5 meters away from point P as indicated in the figure. Then they were saying calculate the electric field at point P. One of you should also send the question paper for 2024, first one. We're actually supposed to just do this question papers because I think it's the best way to practice. Okay, with electric flux, we'll start. Okay, electric flux, we'll do it on the next session. Today, I had a long day. We're supposed to do everything today, so that's fine. We're supposed to do both topics. So let's see, this one, they're saying a charge of 4 microcoulomb is placed at a distance indicated. Calculate the electric field. So here it's a matter of you knowing how to calculate the electric field. It's calculated as kq over r. R what? R squared. Remember from this one, from this formula, so they just took 1 square. So you only take this part. So this part represents the electric field. I hope you get it. Between 2-point charges, no? So here you're going to say K, you know it's 9 times 10 to exponent 9. Q1 is 4 times 10 to exponent. You'll convert that to 3. The radius is 2.5, then squared. You'll get 5,75, which is this one, times 10 to exponent 6 Newton per coulomb. Yeah, and don't forget to write the unit, especially on long questions. With this one, the unit we know it's newtons. So yeah, the value that you get is this one. So it means this is a. So this one, remember, it is what? It is a point charge, no? To the right. Which one will move to the right? It's a test charge, this one. So they are saying 5,76 times 10 to exponent 6. So it will move in this direction. Due to this, it means that this point charge was negative. Then now, you know that the answer here is letter D. Then we'll go to number 8. 2-point charges Q1 and Q2 are separated by distance. Calculate the net force. So this one, it's very easy. You just calculate like this. So this question paper is very easy. It's supposed to get total here. As long as you knew that theory, because I think most of you will not read when you're writing this to exponent 9. But this one you will repeat it twice. Times 10 to the power negative 9. Then the radius is 4,2, which we know it will be 4,2 times 10 to the power negative 3. Fine. Then you get your answer, right? And remember, guys, on the exam, they won't ask much of, let me say, much of calculations based on one topic. So yeah, so don't stress and don't worry. We're gonna get there. When should we have our contact class, guys? Okay, we'll discuss it in the group. It's fine because here we're busy. Then this is squared. Oh, this is in coulomb per meter. Dot meter. The final answer. As I can see, the value I'm getting is 0 point something. I don't know. Were we supposed to convert this one? Let me see if I don't convert. We're not supposed to convert it. Okay, when you don't convert, you'll get force to be 1,033 times 10 to the negative 8. Even. How did they get this value? The net force. Okay, that's what you're going to do, right? You'll say force equal to, oh, I placed the wrong 0,5 times 10 to the negative 9. This one is you can even say squared, but let me not write the square, write it twice. 4,5 times 10 to the negative 9 all over. So this is 4,2 times 10 to the negative 3. So you'll get 10,3. I'm getting 10,3 times 10 to the negative 3 newtons. So we must convert this. This guy, we must convert him to what? Coulomb per meter. The answer here is coulomb per meter. Guys, how do you get these units? Anyone with an idea of how we're supposed to build this one? Okay, it means we'll start at we'll stop at number 12, because that one is electric flux. Then, okay, and then we'll try doing this one. Question 2, 2.2. Or we should convert this one to meters, right? Let's convert that. It's 4,2. Oh, we have already converted it. It is in meters. So how did they get this coulomb meter? Guys, the unit for force, we all agree it's force per meter squared. So to move from here, no, is it Newton? Check something. For force is newtons, no? So coulomb per meter, how do you get this? Or you all don't have an idea? Okay, in the meantime, let's do number 9. When you are still thinking about this one, let me do this. I want us to stick to one question. Then number 9, they were saying when a neutral and charged object is placed close to another neutral object, what will happen to the electrostatic force? So this one, it says the first option, the electrostatic force will be attractive or it will be repulsive. Then the two objects will apply equal forces in the opposite direction. Then number D, they were saying the electromagnetic force is 0. Someone's electromagnetic force. So guys, you see this theory is very important. That's why I said you must check that theory of a charged particles, and they will mean this ones. Ish, I hope it doesn't lose. Yeah. Properties of electric charges. So you must make sure you check them. Ne? All of this and also this part. So let me go back there. So a neutral object. So we've got two objects which are neutral, plus, minus. So they've got equal number of charges. So what will happen? Are they going to so if these objects are equal, it means their force is equal as well, right? So it means their forces are equal. That's what it means when they say these objects are neutral. Even the force will be the same, right? So the answer is letter C, because this one is the only one that's saying the two objects will apply equal forces in opposite direction. So they'll repel each other. So with the magnetic force, we're not sure about this one. I don't think it will be zero. It will be letter C, this one. I don't know if you guys actually chose C here. Then we'll go to number 10. They were saying two equal small plastic spheres having positively electrical charges are given when they are 30 centimeters apart. So you've got two spheres, 1, 2. Then they are 30 centimeters apart. Then they give you the repulsive force between them. Just say FR 0,250 Newton. Calculate the charge on each sphere. So this one is quite easy, right? You'll just say F equal to K Q1 Q2 over R12 squared. We know that since they are the same, they've got the equal charges. So it means K1 and K2, they are the same. So you just have Q squared there over R squared. And then you calculate. Your force, you already know the value, right? The value of force is what? 0.250 K 9 times 10 Q. Then you'll just make Q subject of the formula. And you get your answer. The distance is 30 centimeters, so it will be 30 times 10 to the power negative 3. Like that. And then you get the value of Q. So you'll be having this. We'll just divide it. No? Then you do the square both sides. So the value of Q will be 80 times. So guys, what time are we knocking off? 9 times 10 to exponent 9 times 10 to exponent negative 7 coulombs. So this topic is very easy, guys. I don't know if you guys will struggle to pass. If you fail test 1, I don't know. Hey, why am I getting? Oh, this will be negative 2, not. I converted this wrong. It should be negative 2. We're converting to meters. because this should be 2, negative 2. Yeah, you'll get 2,88 coulombs. So that's the charge. Was I? We're still here, right? So we're having this one. So this is the most possible answer, right? Letter C. I don't know if you guys got letter C on this one. Am I getting wrong values times 10 negative 12 negative 2 divided by, yeah, so the answer here will be letter C for number 10. Then number 11, a proton is released from rest in an electric field. Then calculate the acceleration of the what? Of the proton. So the formula for electric field, I didn't capture that part. Okay. It's given by force. We know that we've got E times the charge, right? This is the formula. And then the electric field, 200 times 10 to exponent 4. Then for the charge, right? So this will be the charge of the proton. So is that constant? It's 1 comma something. Calculate the acceleration. Okay, now we're still calculating the force. Let me see what's the value there on the table. We're just supposed to come to the table and check this value. Charge on a, yeah, it will be 1 comma 6. They are the same. The charge of an electron and a proton are the same. So I'll start by getting the force, right? So the force will be 10 to exponent 4, 1 comma 6, 10 to exponent -9. You'll get 3 comma 2 times 10 to exponent -13. So this will be your force. Then from here, after knowing your force, you're gonna use the formula F equal to MA. Then you substitute. For the mass, although are not given, we'll use the mass of a proton. So it will be, we know that now we can say F equal to MA. Then the force is 3 comma 2. Then you put the mass of a proton. It's 9,11 times 10 to the power -31 times 10 to the power -31. Let me do that. So you'll get, is it -31? Electron mass. No, I took the wrong mass. Ne? It should be this one, 1,66. So let me just write it here. 1,66 times 0.6726 times 10 to the power -27. This one is the mass of a proton. So the charges are the same, but their masses are different. So then I will have this. Then you multiply by the acceleration. -27. Then you'll get 1,9. 1,91 times 10 to the exponent 14. meters per second squared. So the answer here was letter A. So for now, let me stop here because the next question they are asking about the electric flux. Ne? So we'll stop here. Then this one, I think, let me see. Q1, Q2, Q3. Right. So okay, let's do 2.2. Ne? With the electric field, let me see. The electric field definition I've already shown you. But let me look for a simple one. And you must also know how to state Gauss law. So this is how you'll define electric field for question 2. I don't know if you guys, is there anyone who has the simpler definition for electric field than the one that is there on the what? On that document. Okay, I'm having this one, a region of space around an electrically charged particle. Yeah, I think this is easy. You just use this one. Yeah, I know this one now, 2.2. They're saying in an XY plane, charge Q1 is located with on that distance from the origin on the x-axis. So you are having charge Q1 and Q2 is on this side and charge 3 is located somewhere here. Q1, Q2, Q3. Then they said draw a force diagram showing the electrostatic force exerted on what? So yeah, you must also consider the signs. So Q3 is positive. All of them they are positive, positive, positive. So the first diagram showing the electrostatic forces exerted on Q3 by Q1. So they were looking for this part. I wanted you asked to show the electrostatic force acting between those two. First diagram. So we know that there will be an electric field acting between these two particles, right? It's 3, 1. And here we'll have another one, E1, 2, E2, 3. So meaning that and we know that the charge here is 1,21 nanocoulomb. With Q2, they all have the same charges if you check. And this one will be 1,2. So they are going to repel each other, right? 1, 3. So we know that we have got F, the force acting between charge 3 and 1, and the force acting charge 1 and 2, and even here the force acting between 2 and 3. Let me write that. So since there is a repulsion, they are going to cancel each other, right? So let me try drawing. So 2.2. The first diagram, the x component. Okay, this is what we are having there. This is Q3, Q1. They have the same charges. Okay. Here we've got F31. So now we can draw the components. No? This one, no, it will be pushed downwards. So here we're going to have what? This one will be our Y. Which one will be our Y? Remember this, so this is like this. No? It will be the x-axis, x, y. Yeah. Then this one, this part will be our x, f of x1. Then here we'll have what? The y component. No? This one, the y component will be here. Guys, can you also comment a bit here so that we draw the right thing? And this thing just had 1 mark. 1 mark. So I don't know what actually they were looking for here. Okay. Guys, how did you draw the diagram here? This thing had 1 mark, guys. I thought I'll come up with something that makes sense, but hey, the other one is here. This one is F2, Q2. So here we'll have our Fx2. All of them, they are positive, isn't it? So if all of them are positive, guys, where will be the y component? Let's focus on y2. Where will be the y component for Q2? They will both be here. I know the question didn't ask this partner, but you must know it. Let me just check here on your slide. In positive. Yeah, I wanna see this part. Pushed. Oh, but this is what they wanted here. They just wanted us to write this. This is charge Q3. Let me do this. Positive, and this is Q3, Q2. No, Q1 and Q2, Q3 and Q1. Yeah, they just wanted you to say F13. Then here, this one will go this side, this one will go this side. And then here you'll have what? Yeah, you were supposed to draw something like this, guys. Then you get your 1 mark. No? Showing the electrostatic forces on here. For you showing that this direction, the important part was showing this, and also indicating that the force between these two guys, it lies between this part. So that was the only thing that they wanted. Then 2.2, they wanted you to calculate the electrostatic force on Q3 by Q1. and Q2. I think this one is very easy. It's a matter of you. Okay, yeah, I'll use this diagram. Yes. The distance is what? Negative 230. Okay. So now doing 2.2.3. Calculate the magnetic net force. Okay, calculate the X and Y components. Oh, guys, give me 2 minutes. Yeah. Okay, guys, let's stop here for today. I wanna go and do something at the lab. So for today, let's just stop here. We'll continue.